In this lecture, we are going to discuss the chapter 13, which is nuclear reactions. We will focus on nuclear equations, type of radioactivity decay, radiation units, and also we will discuss the nuclear fission and nuclear fusion. In this picture, we can see two units of the three units of the Palo Verde nuclear generator station in Arizona. Then these three units can generate energy to meet the electrical needs of about 4 million people. Then in this lecture we are going to answer this question: how do the nuclear power plants get the energy? And before to answer that questions, we need to know some general concepts. And first start we will talking about the nucleus. And we know the nucleus consists of protons and neutrons, but because the protons they have light charge, both are positive, and we know they will try to repel. Yes. But why, if the protons they are on light charge and according to the electrical force they will repel, then why the nucleus stick together? Then the answer is there is another force that is larger than electrical force, and that force is called the nuclear force or the strong force. That force, the nuclear or strong force, is the force that holds the nucleus together. That force is greater than the electrical force. That force, the nuclear force, is about 10 million times stronger than the chemical binding that holds the atoms together in the nucleus. And another point I would like to discuss is this force is a strong force but act in a small distance. If the distance between two protons are larger than 2.5 10 to the power minus 15 meters, then that force is very weak. Then the distance between two protons, if we had here two protons, and this is D, the distance is larger than 2.5 10 to the power minus 15 meters. Then the nuclear force is really weak. The nuclear force is weak. And then what happened is, because of this limitation, because the nuclear force is really small, is weak, when the distance between two protons is 2.5 10 to the power minus 15, this condition limits the size or defines the size of the nucleus. This is why the size of the nucleus is the order of 10 to the power minus 15 meters of femtometers. Yes. Now we can answer the question: how do the nuclear power plants get the energy? And remember, when we discuss the work, we define the work equals to force multiplied by the distance. But work is related to energy, and this is why work and energy, they have the same units. The units are joules. Then what happens is, when the nucleus break apart into two or more light nucleus, energy is released. This is why the nuclear force, keep holds the nucleus together, play an essential role in the starting energy that is used in the nuclear power plants and the nuclear weapons. Then this force, yes, because of this force, then when the nucleus breaks, generates some energy. Then the energy that is released by one nucleus is a small energy. But what happens when we add the energy that is released for billion of nucleus, then the amount of energy is huge amount, is significant amount of energy. Now let's talking about the atom size versus nucleus size. Then the atom size is about 10 to the power minus 10 meters, means is 1 angstrom. And the size of the atom is 1 angstrom. The size of the nucleus is 10 to the power minus 14 minus 15 meters, depend of the element. What we can see is the size of the nucleus is 4 orders of magnitude smaller than the size of the atom. And maybe we can explain better this one. For example, if this is this, we can compare this one with these measurements. If we had, for example, here we had here 1 meter. Sorry, we had here 1 meter. Then the size of this one is 4 orders of magnitude larger than the size of the nucleus. Then here will be something like 10,000 meters. It's 1, 2, 3, 4 zeros. Then in this proportion is also the size of the atom with the size of the nucleus. Yes, it's like if we had 1 meter, then here we had 10,000 meters. The difference is huge. Yes, it's 4 orders of magnitude. And we can compare, this is the same happening. Here is 10 to the power minus 10. Here is 10 to the power minus 14. Yes, it's 4 orders of magnitude smaller. But in case of the electron, the size of the electron is compared with the size of the atom is 8 orders of magnitude smaller. And in this case, it's like if we had here 1 meter, yes, if we want to compare in this the same way, in case of the electron, yes, if we had here 1 meter, here we will have 8 zeros. And in this we'll add 100 millions, yes, the size, the difference here is meter. If we had here the 1 meter, the size, if we had 8 order of magnitude difference, when we had here 100 millions times larger. Yes, the size of the atom is 100 millions times larger than the size of the electron. And we can see there are huge difference between the size of the nucleus and the size of the electron compared with the size of the atom. And it's just, I want you had idea about the sizes, the sizes of the different part of the atom. Then also another good comparison is, if this is the nucleus, is a penny is a nucleus, then we can think the atom is like the football field. Yes, it's just, you can think you are trying to find a penny, yes, in a football field. Yes, and you will have a lot of work if you want to find that, because is the difference in sizes are huge. And it's the same happen with the nucleus and the atom. Yes. Now let's talking about the mass. And what happened is the mass of the proton and the mass of the neutrons are very similar. Yes, we can see here is 1.672 and here is 1.675. 10 to the power minus 27 kilograms, but the mass is small. Yes, it's minus 27 kilograms. And what we can see is these two masses are almost the same. But what happened with the mass of the electron is 9.109 10 to the power minus 31. Then it's 4 orders of magnitude smaller than the mass of the proton or the neutron. And in this case, we can think if the mass of the proton is, we can do some comparison. If the mass of the proton or neutron is 10,000 grams, yes, kilograms, sorry, then the mass of the electron will be 1 gram. Yes, this is 1, 2, 3, 4 order of magnitude larger. Yes, it's more or less the same proportion. Then if the mass of the electron is 1 gram, the mass of the proton or neutron then will be 4 order of magnitude larger than the mass of the electron. And we can do this comparison. If we had something with 1 gram, then 4 order of magnitude larger is 10,000. Here, sorry, it's kilograms. Let's use the same unit. If we had something with 1 kilogram, then 4 order of magnitude larger is 10,000 kilograms. Again, this is just, I want to make some comparison. In this way, you understand the difference between the mass of the proton or neutron is huge. Yes, is huge. Then this is why when we calculate, when we need to calculate the mass of the atom, just we need to take into account the mass of the proton and the neutron, because these are the significant mass in the atom. However, the mass of the, we don't need to take into account the mass of the electron because it's really small. Yes, it's like if you add 10,000 plus 10,000 is 20,000, but if you want to add just 2 kilograms, it's really a small quantity. And then this is why the mass of the atom is just the mass of the proton plus the mass of the neutron. We don't take into account the mass of the electron. And let's see what we had in the next slide. Then now we want to discuss about the nuclear reactions. Then the first person that studied and discovered the nuclear reaction was Becquerel. What he did is he placed an uranium mineral in a photographic plate, like we had here in this picture. Then what he found is a silhouette of the mineral on the plate when it was developed. As when the plate was developed, he found a silhouette on the plate. Then what he concluded is there is something was emitted from the mineral, and that time he didn't know what kind of radiation was emitted. Then he called this one radioactivity. And he was the first person that studied the nuclear reactions, yes, or radioactivity. And later, Ernest Rutherford, he discovered that were 3 kinds of radioactivity. Now we know there is more kind of radioactivity, but in this course we will focus on these 3 kinds of radioactivity. Then that happened. This radioactivity happened when we had unstable nucleus, yes, and this become more stable. Then some reaction happen. What kind of reaction can happen? Can emit, to be more stable, emit some energy or emit some particles. Then in this case, if the nucleus emits 2 protons and 2 neutrons, then this called alpha radiation or alpha particles. Then the other one is just to be more stable. When the nucleus of the element is unstable, to be more stable, emits some energy, then this is called gamma radiation. And in the third case can emit beta particles which correspond to an electron, high energy electron. Then there is 3 different kind of radioactivity or nuclear reactions can be alpha, can be beta, or can be gamma. Then another thing is, remember, the strong force is that keep the nucleus together. Yes, keep the nucleus together. Then there is another force, that weak force, which is the responsible for the radioactivity decay, or we call nuclear disintegration of the atoms. Yes, that weak force is responsible for the nuclear disintegration. Then here I want to establish the difference between the chemical reaction versus nuclear reactions. That chemical reaction that we studied in the last chapter, we can see in the chemical reactions we had the same elements on one side and on the other side of the chemical equation. Yes, we had the same elements in the reactants and the same elements in the product. We had carbon, carbon, we had oxygen, oxygen, we had hydrogen, we had hydrogen. Just how they react for a new compound is what we had from one side to another side. But in case of the nuclear reactions, what happens is the protons and the neutrons are rearranged in the nucleus, and that happens is in the product we will have a new element. Yes. Then here we had iodine. Yes, we had iodine here represent the nucleus of the iodine, and when the nuclear reaction occurs in the products, we had a different element. Yes, and some energy or some particle that is released due to the nuclear reaction. Then in chemical reactions, we had the same kind of atoms in the reactants and the products, but in case of the nuclear reactions, we had different kind of elements in the reactants and the products. Another definition that I would like to review is the isotopes. Remember, the isotopes are elements that have the same number of protons, but the number of neutrons can be different. Yes, can be varied. And for example, we in this diagram, we had different isotopes for hydrogen, and we can see the number of protons is the same because it's hydrogen. However, the number of neutrons can change. Yes, and we discussed last time we can represent the isotopes using the nuclear symbol, and in the bottom part we had the atomic number, which is the same as number of protons, will be 1. Yes, we had here 1, 1, 1, and mass number is the number of protons plus the number of neutrons. Then this is why here is 1, 1 plus 1 is 2, this is 2, 1 plus 2 is 3. Yes. Another way we can express, or we can write the isotopes are in this way. We can write aluminum and then 25, where 25 is the mass number. Or we can write just the symbol and then the mass number. And in this example, we want to find the number of protons and the number of neutrons of the nucleus in the nucleus, and the nuclear symbol of the aluminum 25. Yes. And to do that, we need the periodic table. Why? Because we need to know the atomic number, and we know the atomic number is, for the aluminum, is 13. Yes, it's this number we have right here. Then now we can write the number of protons if we have the aluminum 25. The number of protons, let's start with the number of protons. is 13. And why we know? Because here is the atomic number. Yes, it's 13. And we know the way we can find the number of neutrons will be 25 minus 13, which is 12. It's 13, 12. Then now we can write the nuclear symbol. And the nuclear symbol, then we know the number of protons on this part and the mass number is on top. This will be the nuclear symbol. Then we have the number of protons, the number of neutrons, and the nuclear symbol. And we need to know this one. We need to know this to understand the nuclear reactions. Then now we are ready to discuss each type of radioactivity decay. Then let's start with the alpha decay. Then this is a radioactivity process in which a particle of 2 neutrons plus 2 protons are ejected from the nucleus of a radioactive atom. Then in alpha decay, one particle with 2 neutrons and 2 protons is ejected from the nucleus. Yes. Then what happened is we had this nucleus which is unstable, has many protons, many neutrons. To be more stable, this nucleus ejects the alpha particle. Then the alpha particle is just 2 protons and 2 neutrons. Then now we will see why we can express the symbol of the alpha particle like that. Yes. First, because 2 neutrons and 2 protons correspond to the helium nucleus. Yes. This is helium is number 2, then it has 2 protons and 2 neutrons. And if we had just 2 neutrons and 2 protons and 2 neutrons, we will have just the helium nucleus. And this is why one symbol for the alpha particle or alpha radiation is helium. Now, because we had 2 protons and 2 neutrons, yes, here is the number of protons we had here, or the atomic number, yes. This is why we had 2. Now, if we had 2 protons, yes, I will write here, 2 protons, yes, 2 neutrons. We add this one, we will have the mass number, which is on top, yes, is 4. Then this is the nuclear symbol for the alpha particle. Yes, we had helium, then 2 correspond to for atomic number or just the number of protons. And if you add the number of protons plus the number of neutrons, you had the mass number, which is on top. And you can use this symbol. You can use this symbol to indicate also the alpha particle. Again, now you know why we had 2 and 4 here, or just the alpha particle. And in your book, they use this symbol, then we will use the same symbol, use it in your book. Then what happens is when this unstable nucleus ejects this particle, then now because the number of protons change, this is why we will have in the products, we will have a different element. Then now what we will do in the next slide is we will learn how we can write the nuclear equation for alpha decay. Yes. Then now we want to write the nuclear equation for the nuclear reaction of these isotopes that decay emitting an alpha particle. Then we had here plutonium, which is the same we had in this example. We had plutonium-240. And then we want to write what is the nuclear equation. Then the first thing we want to know is we want to write this one. We want to write the symbol for the plutonium in a nuclear symbol. To do that, we need to know the what is the atomic number, and for that we need to use the periodic table. Then the atomic number for the plutonium is 94. Where is this here? Yes, it's plutonium is 94. And we know this is the mass number. Yes, this is the mass number. Let's write first the symbol for the plutonium. Then plutonium will be at 240. And here we will have the atomic number, which is 94. Now let's write now the number of protons. We know is, in this case, is 94. The number of neutrons, then it's 240 minus 94 will be 146. Then what happened is, if this isotope decay emitting an alpha particle, remember it's emitting 2 protons and 2 neutrons. Yes, 2 protons and 2 neutrons. Then any element we had here, yes, the number of protons will be 94 minus 2. Yes, because emit 2 protons, then that plutonium lose 2 protons to be more stable. And we had 92 here. Here is protons, sorry. Here is protons. Also, to be more stable, the nucleus of plutonium emit 2 neutrons. Then we will have here 146 minus 2 will be 144. And whatever we had here, we had 92 protons, and the mass number we need to add this one will be 6, will be 3, will be 236. Then we had here that has 92 protons plus and 236 as mass number. Then to know that, yes, we don't know what we had here, but we know it's 92. The mass number is 236. And this emit the alpha particle. And we know this is the symbol for the alpha particle. Then to know what the element we had here, what kind of isotope, we will use the periodic table. Then it's 92 is uranium. Yes, is uranium. Because this is telling what kind of element, the number of protons or the atomic number is 92. Then now we know here what we had is uranium. Yes. And this is the nuclear equation for this nuclear reaction. Yes. Now let's try the next one. Then we will do the same thing. We will follow exactly the same procedure. And in this case, we had uranium. And we know the mass number is 233. And to know the number of protons or the atomic number, we will use the periodic table, which is 92. It's 92. And now we can write here, in this case, we had 92 protons. And to get the number of neutrons, we will subtract 233 minus 92. Yes. Probably I will write here then 233 minus equals to 141. Next, 141. Then here what we had is something that we don't know, yes, plus alpha particle. And what we had here, we know the number of protons will be decreasing to decrease by 2, because uranium, to be more stable, release 2 protons and 2 neutrons. Then we will have 92 minus 2 will be 90. And the number of neutrons will be 141 minus 2 will be 139. We add this one together, will be 9, 12, 2. 229. And we will have something here. What element? Yes, we will have here an isotope with atomic number will be 90 and the mass number 229. And to know what kind of isotope we had here, we will use the periodic table. The 90 is thorium. Yes, it's here. It's thorium. Then we will write here thorium. And this is this one. They are the nuclear equation for this nuclear reaction. What I want you to notice here, now we can analyze each of the equation. What happened if the alpha decay occur? Then you see that the atomic number will be decreased by 2. You see 94, 92, 92, 90. Then the atomic number will be decreased by 2. What happened with the mass number? Will be reduced by 4. Yes, 240, 36, 233 to 229. Then we can use a rule, and we don't need to do all these steps. Yes, I did this time because I want to explain. I want you know why we can use this rule. But now we can use this rule. Then what happened if we had alpha decay? If we had alpha decay, the mass number will be reduced by 4 and the atomic number will be reduced by 2. Yes. In this way, we will know what is the new isotope we had in the products. And let's try to apply this rule to get the nuclear equation for another isotopes that decay emitting an alpha particle. One thing is, if you want to write all the procedure is okay, but if you want just use the rule also is okay. Then let's try to apply the rule to write the nuclear equation for polonium and for plutonium for this particular isotope of polonium. And polonium, we had here polonium. We had 2. This is the mass number. To know the atomic number, we need to look at the table, look at the periodic table. Then polonium will be 84. And let's see, what is the 84? This must be here. Polonium, yes, 84. Then we can write here 84 for polonium. Then what we had here, and according to the rule, the mass number will be reduced by 2, but the mass number will be reduced by 4. Will be 208 minus 4 will be 204. And we know here we had the alpha particle. And let's see, 82 correspond to lead. Yes. Then the polonium, to be more stable, decay in lead isotope. Yes, lead. And this is the equation for polonium. If the polonium emitting an alpha particle. Let's try it for plutonium. And we have plutonium 242. Now we know plutonium is 94. Is here. Yes, plutonium is here. Is 94. And now we can write the new equation. This is 94. And the new isotope will be had as atomic number will be 92 minus 2, because it's reduced by 2, we will have 92 here. And the mass number will be reduced by 4, will be 238. And we need to check 92 correspond to uranium. And we will have here also alpha particle, yes, because this is the way this become more stable. Yes, it release alpha particle and then the plutonium is decayed in uranium. I want just to write here, you see, this equation. Then I want to write here the equation we got. This is the solution for this problem, okay? But I want just here, because I want to discuss something, then I want to write here uranium 92 to 36. That what we can see here is, this is 94. Here we had plutonium, however, the mass number is different. Here we had uranium, however, the mass number is different. And the reason is the mass number is different is because they are isotope of uranium. Remember, each element is identified by the number of protons or the atomic number. This is why if we had uranium here, these numbers must be 92. Yes, because this is identify what kind of element you had. But the mass number can change depending of the number of neutrons. Yes, and in this case, these are the same element, but the number of neutrons in the nucleus is different. This is why the mass number is different. Remember, mass number equals to the number of protons plus the number of neutrons. If the number of neutrons change, then the mass number change. This is I want to show here is, even if we had the same elements, but the mass number is different because the number of neutrons in each isotope change. The second nuclear reaction we want to discuss is the beta emission. Beta emission occurs when a neutron turns into proton, as neutrons turns into proton by emitting a high energy electron plus high energy electron. And this high energy electron is called beta particle. And we can represent this reaction we had here using symbols. Then the symbol for neutron is the N, and we had here 0 and 1. Then why we had 0 here? Remember, in the nuclear symbol, this represents the number of protons, or the atomic number as the number of protons. And this number represents the mass number. Which is protons plus neutrons. Yes. Because we don't have any proton and we had one neutron, this is why here is 1. In case of the protons, we had 1 proton, yes, this is why we had here, and the mass number is protons plus neutron. We don't have any neutron, this is what we had here, just one proton. In case of the beta particle is high energy electron, this is why we use the E here, but the electron doesn't have any protons or neutrons, this is why we had here 0, and -1 is related to the charge of the electron. Then remember what happened in beta emission is 1 neutron, yes, is turned into proton plus high energy electron. And remember when we discussed about the mass of the proton and the neutron was a slight difference between these two. Because of this slight difference, this is why when the proton is turned into when the neutron is turned into proton, we had here some additional particle, yes, which is an electron, high energy electron. Then what happened in beta emission? Remember, we had unstable nucleus here. In this case, we had unstable nucleus of iodine. And to be more stable, one of these neutrons is changed into proton, yes. And in this, when this happens, one beta particle is emitted, yes. And this is how we can write the equation. Then we will have something like that. Yes. Iodine is changed into xenon plus beta particle. Then we can use this symbol, which is also is used in some books, or we can use the other symbol. In your textbook, they use this symbol, then let's use the same symbol is in your textbook, and we will use the bottom one. Then how we can get this equation? And how we can get the equation for beta emission? Then we will learn in the next slide how to do that. Then we want to write the nuclear equation for the beta decay of the following isotopes. And if beta decay occurs, yes, if one neutron is converted to proton, then what we want to write, what is the nuclear equation in this case. And the procedure will be followed is similar to what we did before. Then we add here the iodine, and we know here 131. Then the iodine is 53, is here, yes, it's 53. Then again, the way we will write the nuclear symbol, we need to use the periodic table. Yes, we need to find the iodine and we need to write. Then we need to write, in this way we can write the nuclear symbol. And we know the number of protons is 53. The number of neutrons will be 131 minus 53, which will be 78. Then when this happens, one neutron is turned into proton. Yes. Then what happened with the neutrons? The neutrons will be, then the iodine will be lose one neutron, then will be 78 minus 1, because lose one neutron, but gain one proton. Yes. Then will be had here 53 plus 1 will be 54. Then if we add these two, we will had 11, 13 will be 131. And now we know what we had here will be the number of protons will be 54, and this is 131, and the mass number will be 131 plus beta particle. Plus beta particle. Now to know what isotope we have there, yes, we need to check that in the periodic table. Then 54 corresponds to the xenon. Then we know here this is xenon. Let's do the same thing with the next one. In this we have carbon 14. Then we know the mass number is 14. To know the atomic number or the number of protons, we will check in the periodic table, which is 6. 6. And now we know the number of protons. Here is 6. The number of neutrons will be 14 minus 6 will be 8. Then when the beta decay occurs, we know one neutron is converted into proton. Then the new element, we had 8 minus 1, which is 7. Lose one neutron, but gain one proton. There will be 6 plus 1 will be 7. Then the mass number will be 14. Then the new element we had here will be 7 protons and 14 mass number, plus release 1 beta particle. And we need to check here 7 correspond to nitrogen. Now we can analyze both equations. Then what happened with the number of protons? What happened with the atomic number? Yes, is increased by 1, because 53, 54, 6, 7. This is increasing by 1. What happened with the mass number? It's the same, yes, doesn't change. Yes, it's 14, 14, 131, 131. And now we can write the rule for beta decay. Then what happened if we want to write the equation? What we need to take into account? The mass number is stay the same. We don't add. We don't need to add or subtract anything. But for the atomic number, we need to add 1. Yes. And again, if you want to write the complete procedure, you can write the complete procedure, or you can use the rule to write the nuclear equation. Then let's now try to write the nuclear equation for the beta decay of the following isotopes, but this time we will use the rule. And let's start with the phosphorus. And for the phosphorus, we have 32 as the mass number. And let's write here phosphorus 32. Then now we need to check what is the atomic number. The atomic number is 15. Let's see here we have 15. Yes. And if the beta decay occur, then we will have here the new isotope will have the same mass number. Yes, because we don't need to change anything. It's the same. But the atomic number we need to add 1. Then will be 16. Plus beta particle. And now we need to check what is 16, which is sulfur. Yes, and here we have sulfur. Then let's try the second one, is gold. Yes, we have gold. And we have gold here. The mass number is 201. Now we need to check what is the 79. Yes, it's here. It's called 79. Then if the beta decay occur, the new isotope will have the same mass number, but the atomic number will be increased by 1. Then we will have 80 here. And in the nuclear equation, we will have the beta particle. Then let's check what is 80. It's mercury. Yes, we have here mercury. Then, and this is the nuclear equation. Now let's go with the last one. We have sodium. Sodium, the mass number is 24. To know the atomic number, we will check in the periodic table, and is 11. You have here is 11. And if the beta decay occur, and the new isotope here will have the same mass number, but the atomic number will be increased by 1. We have 12 here. And then we will have here also the beta particle. Then 12 corresponds to the magnesium. Yes, and we have to write here. Let me write better that one. Write better magnesium. Yes. And these are the nuclear equation for these 3 isotopes if they decay. If the nuclear reaction occurs with beta decay. Then the last nuclear reaction we want to discuss is the gamma emission. The gamma emission is the high energy electromagnetic radiation from an excited nucleus. And again, all these different radiations, or they emit or eject particles, the nucleus, they eject particles or emit energy to be more stable. And for example, here we have the plutonium, then the plutonium to the nucleus of the plutonium to be more stable, what is just radiation energy. And this is high energy radiation, correspond to gamma. You remember gamma in the electromagnetic spectrum? Now this is high energy radiation, yes, high frequency, low wavelength, yes, this is gamma radiation. Then how we can write the equation? How we can write the equation if the gamma decay occur? Then, because in this case just the atom, the nucleus of the atom emits some radiation, there is no change in protons, there is no change in neutrons. It's just because emit energy, the nucleus become more stable. Then how we can write that? Then this asterisk here indicate this is excited state of the plutonium. Because there is no change in protons, there is no change in neutrons, then there is no change in mass number. Then we will have the same plutonium, but without asterisk, means now plutonium has a lower state energy, but emits some energy. What energy? Gamma emits some radiation. What radiation? Gamma radiation. And this is the symbol for gamma radiation, because there is no mass number, there is no protons, there is no neutron, because it's just energy, and this is why we had 2 zeros here. Yes, this is the symbol for gamma. Then this is the equation for plutonium. This is the nuclear equation if the plutonium decay is more stable through gamma decay. Yes. And let's try to write the nuclear equation for the gamma decay in each of the following isotopes. Because we had radon, we had iodine, we had cobalt, and we had barium. Let's try with the first one. And for this one, we know here we need to write the mass number, yes, and the atomic number. We need to check that in the periodic table. In this case, is 86 here. Yes, it's 86. Then let me write these numbers. We had here in this case 86. And this is excited state of the radon. And then this radon emits some alpha particles, then became more stable, but without changes the number of protons, the number of neutrons. This is why these two numbers are the same. But because it's more stable, then this is more stable because emit the gamma radiation, and this is the symbol for the gamma radiation. Let's try for iodine. We had here the mass number, and the atomic number we will check here, which is 53. Yes, here is iodine. Here is excited state. But now here we have the lower state energy without change the protons and neutrons, but here emit alpha radiation. In case of the cobalt, we had 16, we had, let's see, 27 is cobalt. This is here 27. This is excited state, and to be more stable, release gamma radiation, and now we had the same isotope but more stable with lower energy plus gamma radiation. And the last example is barium, and we had here barium 137 is the mass number, then the atomic number is 56. Yes, this barium is here 56, and this is excited state of the barium, and now it's more stable because emit the alpha radiation. Now we have the same isotope but with lower energy. Yes, with lower energy. Let's right here closer. And these are the nuclear equation for each of these isotopes if the gamma decay occurs. In this picture, we want to show the type of radiation versus the penetration. Then here we have the alpha rays, and the alpha rays, we can stop alpha rays using just a paper. In case of the beta rays, we can stop beta rays using a thin metal sheet or thin metal of aluminum. Gamma and X-ray, we can stop using a thick lead or steel plate. But neutron rays, we didn't discuss the neutron rays, but in order to stop this kind of radiation, we need water or thick concrete wall. Then this is why the energy of this radiation increase from top to bottom. Yes, the more energetic radiation corresponds to the neutron rays. This is why most of these radiations are dangerous for us. Here in this slide, we can summarize the 3 different types of radiation of the radioactivity decay we discussed in the previous slides. Then we had alpha emission, and we know we had alpha emission, the number of the atomic number will be reduced by 2, and the mass number will be reduced by 4. And we need to write always the alpha particle in the equation at the end. In case of the beta emission, the atomic number will be increased by 1, but the mass number stays the same. And we always need to write at the end the beta particle symbol. Yes, in the equation we need to add the beta symbol in the equation. For the gamma decay, we know there is no change in proton or neutrons. Just what happened is there is change in the energy in the nucleus. Then this is why the atomic number and the mass number stay the same, but this asterisk means here we had excited state, here we had lower state of the same nucleus. Plus, we need to add the gamma radiation symbol. Yes. Here we summarize the 3 types of radioactivity decay. In this diagram, we had the electromagnetic spectrum, and I want you to focus in the last part of the electromagnetic spectrum where we had X-ray and gamma rays. We know the X-ray and gamma rays, they are high energy radiation, high energy waves with the high frequency and shorter wavelength. Then what happens is in some part of the electromagnetic spectrum, we can see the X-ray and the gamma ray, they overlap. Then how we can distinguish between these 2 types of radiation? Then the way we can distinguish is based on their source. Then the X-ray are emitted by disturbance in the inner shell electrons. However, the gamma rays are emitted by the atomic nucleus. Now we know the gamma rays are emitted by the atomic nucleus. And remember, X-ray is related to the electrons and gamma rays is related to the nucleus. Let's talk about the radioactive decay series. The radioactive decay series happen with unstable nucleus like uranium decay in another unstable nucleus like thorium in this case. When this happens, the new nucleus like thorium continues undergo in a series of successive decays until unstable configuration is reached. Then the original nucleus is called the parent nucleus, and the other nucleus in which the parent nucleus decay is called the daughter nucleus. There are three naturally occurring radioactive decay series. One is the uranium decay into lead, the thorium also decayed into lead, and uranium decayed into lead, different isotopes of lead. And let's talking about the first one is uranium 238 decay into lead 206. Then here is the complete decay reaction for uranium 238. And we can see there are different nuclear reactions occur until the uranium decay into unstable configuration, which is lead 206. And also we can see the time in which the decay occur is different also. Yes, some occur in minutes, some occur in days, but other for long time. For example, from uranium to thorium, decay the time of the nuclear reaction is 8.3 10 to the power 4 years. Is long time. And if we add all these numbers, we will get the half-life of uranium 238. And the half-life of uranium 238 is about 4.47 billion years. It's a huge time, yes? And this is why, because the half-life is this big number, then this is why this radioactive decaying chain is useful in dating the age of the Earth. And let's now define and let's now describe what is the half-life. And the nuclear half-life is how long the nuclear reaction takes place. Means how much time takes for the protons and neutrons change, as the number of protons and neutrons change. And the half-life, which this is the symbol, is the time required for half of a sample to decay. And here we had one example. In this plot, we had mass versus time. Mass is in grams and time is in days. This is the radioactive decay for an hypothetical isotope with the half-life is 1 day. And if the half-life is 1 day means is the time required for the sample reduced in half. For example, if we start with some radioactive material, if we start with 1,000 grams, because the half-life of this material is 1 day, then what happened after 1 day? We expected half of the sample. Then we expected 500 grams. After 1 day, we expected half of the sample, which will be 250 grams. And after 1 day, we expected 125 grams. Yes, is the time required for the sample reduced in half. Yes, this is the nuclear half-life. Then the nuclear half-life can be in seconds, can be in minutes, or any unit time can be up to billion of years, yes, as we saw in case of the uranium. Now we will solve some problems which involve the half-life concept. And in this case, if the half-life of the hydrogen-3 is 12.3 days, then we want to calculate how much time will be required to reduce 80 grams of the hydrogen-3 to about 2.5 grams. And let's write here the information we know. We have this equals the half-life is 12.3. Now this is for hydrogen-3. The mass we start is 80 grams, and we want to reduce this mass to 2.5 grams. Then we want to know how much time will be required to do that. Then what we will use now is the concept of half-life. We are not going to use an equation, just we will use the concept. And we know this time is the time to reduce the sample in half, yes? And if we start with 80 grams, then if we reduce this mass in half, if the mass is reduced in half, then that happens in the half-life, which is 12.3 days. And let me write here the time in days. Yes, we don't need to write days each time. Then now, if this sample now is reduced half, then it will take another 12.3 days. If this sample is again reduced in half, then it will take 12.3 days. If this sample is reduced in half, it will take 12.3 days. And if this sample is reduced half, it will take 12.3 days. And to know the total time, or the time is required to reduce 8 grams to 2.5 grams, what we need to do is we need to add the 12.3 all these times, or just multiply 12.3 by 1, 2, 3, 4, 5 times. And we can calculate the total time, or the time required to reduce this sample from 80 grams to 2.5 grams. We multiply 12.3 days multiplied by 5. And the total time will be 61.5 days. And now we can set the time to reduce 80 grams of hydrogen-3 to 2.5 grams is 61.5 days. Let's try one more problem. In this case, we want to solve this problem. If the half-life of thallium-207 is 5 minutes, and we want to calculate how much time will be required to reduce 0.5 kilograms of the thallium to about 1 gram. This is to about, yes, that is important, to about. Then let's write here the information we had. We know the half-life for thallium is 5 minutes. And if we have the mass of 0.5 kilograms, then we want to know how much time will be required to reduce this mass to 1 gram. We want to calculate the total time. Then here we need to pay attention to the units. We had kilograms, we had 1 gram. And we need to convert this one. We need to have the same units. Then we need to convert the kilograms in grams. Will be easy. Then to convert to kilograms to grams, we just multiply by 1,000. Or just remember, you can use the conversion factor. 1 kilogram equals to 1,000 grams. We multiply by 1,000, then we will have 500 grams. And here we want to know the time to how much time we will take to reduce 500 grams of thallium into 1 gram. Yes, this is what we want. And let's start. Yes, about. Yes, let's start. And what we had to do is we start with 500. And this is the mass in grams, and we will write here the time, yes, which is in minutes. Then we start with 500, and to reduce this one in half, we will take 5 minutes. Yes. And now we will do the same, 250. And to reduce this half, it will take another 5 minutes. Then to reduce this one in half will be 62.5. It will take another 5 minutes. To reduce this one in half, it will take another 5 minutes. Then to reduce this one in half will be take another 5 minutes. And then we will continue to divide this one. It will take another 5 minutes. Then 3.90 will take another 5 minutes. If we reduce this one in half, it will take another 5 minutes. And finally, if we reduce this one in half, it will take another 5 minutes. Now we can see this is about 1 gram. Yes, this is we want. Well, and now we want to know how much time will it take to reduce 500 of the thallium to about 1 gram. And we will do the same. Yes, to calculate the total time, we will multiply 5 minutes, the half-life, multiply by, and now we count how many times we need to do this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then by 9. And will be 45 minutes. Yes, and we can, this is the answer. Then we can write the time. To reduce 500 grams of thallium 2072, about 1 gram is 45 minutes. And again, in these problems, we are not going to use any equation. Just what we will do is we'll use the definition of half-life. In the same way, velocity, force, energy, that quantity is half unit. The radiation also has units. But the units depend on what we are going to measure. Yes, if we measure the activity of radioactivity source, then the units can be Becker or can be Curie, and the Becker is correspond to 1 disintegration per second, and this is the units in the SI system. In the Curie units, then we had 1 Curie radiation unit equals to 3.770 10 to the power 10 Becker. Another way we can measure the radiation is the radiation received by a material. Yes, we can measure the radiation that is received by the material. Then the units in this case is the gray, is the units in SI system, on can be rad, which is the radiation absorbed dose. And this is the equivalent between these two units. And the last one is the unit used to measure the radiation received by humans. And the unit is REN, is Röntgen equivalent man. This is the units to measure how much radiation is received by humans. And this is important because in this depend of the value of this unit is this considers the possible biological damage to humans of certain type of radiation. Usually the doses are often expressed in terms of millirem. If the radiation we receive is in REN, yes, then it can be dangerous for us. Then usually the radiation we receive is in millirems. Yes, is in millirems. Just remember here, maybe I will write that is 1 REN equals to 1000 millirems. Right. Millirems. Then we can see in this table is what is the possible effects of when we are exposed on sun radiation. Then the natural background of the radiation we receive in 1 year is about 0.130 REN, or is the same of 130 millirems. This is the radiation we receive from the sun, from the computers, from the phones, from everything that everything at temperature higher than 0 Kelvin emits some radiation. Yes. This is all that radiation we receive is called the natural background radiation. But the upper limit of annual exposure radiation is about 0.5 REN, or is the same as 500 millirems. Yes, we always receive that is the upper limit as we receive, and you will have to complete your annual radiation dose, and you will see the radiation you will, if you add all the different radiation you receive in 1 year, the addition of all that radiation should be around 500 millirems or less. Now, if the radiation we receive is in REMs, then that can be dangerous for us. And you can see here how when the radiation is increases, the effects are dangerous for the humans. And when the radiation is about 500 REMs, remember, just if you want, you add 3 zeros here, yes, REMs, yes, then it can be the lethal dose for the humans. And just in the last part, I want to discuss 2 more kind of nuclear reaction, and this nuclear reaction corresponds to fission and fusion reactions. And both reactions, they produce energy, but how they produce energy or how the nuclear reaction occurs is different. And in case of the nuclear fission, in this case, unstable larger nucleus, they break into a smaller nucleus and release some energy. And they break into a smaller nucleus to be more stable. As is that happen is because the nucleus they gain stability when they break into the smaller nucleus. And this happens with the atomic number is greater than 26. Then here we had the uranium, and the uranium is disintegrate into barium, in krypton, and there is more products we had here, but just this is the main products and 3 neutrons. The main characteristic of the nuclear fusion is in the products we will have 3 neutrons. Yes, 3 neutrons. In case of the nuclear fusion, in order to small nucleus to gain stability, they join with another small isotopes to form a new and stable nucleus, and in this process also the energy is released. And this happens with the atomic number of the elements is less than 26. In nuclear fission, this break into the smaller nucleus, but nuclear fusion, that 2 small nucleus join to form a more stable nucleus. Then in the nuclear fusion, we had here the isotope of hydrogen. They had deuterium and tritium, and they join to form a helium plus neutron. Then how we can identify if we had nuclear fission or nuclear fusion reaction in the equation? Then again, in this case, always we will have 3 neutrons in the products, and this happens in a small nucleus, for example, in nucleus of helium or hydrogen. The nuclear fission is the kind of nuclear reaction is used in nuclear power plants to get energy. Then nuclear fission occurs in nuclear power plants, and nuclear fusion is the kind of nuclear reaction happen in the sun, and this is how we can get the solar energy because of this nuclear reaction happen in the sun. Let's now talking about a little more about the nuclear fission. Sometimes the nuclear fission occurs naturally, but in the nuclear power plants, what happens is the one neutron hit the uranium nucleus. In this way, this get a little more energy and make the uranium nucleus more unstable. And in this way, because it's more unstable, it is easier to break into products. What products? Then usually in this kind of fission nuclear reaction is the uranium is split into krypton and barium and some another more isotopes, but these are the main 2, plus 3 neutrons and energy. Then how we can write the nuclear equation for these reactions? Then in this we had 1 neutron, we had the uranium isotope, and then these are the reactants, and in the product side what we had mainly barium, krypton plus 3 neutrons. Then we can see if in the equation we had on this side 1 neutron and we had heavy or large nucleus, then always we will have in the products we will have 3 neutrons plus few more isotopes. And usually with larger atomic number, as like 36 or 56. And this is the way you can identify the nuclear fission, nuclear equation for fission reaction. In this picture, we had the chain of reaction of the fission reaction, and here we had uranium. This split into barium and krypton plus 3 neutrons. Then what happened is in the nuclear power plants, yes, what happened? They had billions of nucleus of uranium. Then what happened is when the reaction start, when the nuclear reaction start, then this is happened, then this neutron will be also start the reaction with in another uranium nucleus. This also in another uranium nucleus. This is another uranium nucleus, and then they will produce barium, krypton, yes. But this will be also get another 3 neutrons, 3 neutrons, 3 neutrons. Will be continue the chain of reaction. Then what happened is if there is some point, in some point this, if there is no control of this reaction, then the energy that is released is huge, and then an explosion can happen. Then what happens in nuclear power plants, usually they had some mechanisms they can control these reactions. Yes? And this is why they use the uranium as fuel, yes, to get the energy, but they need to control this the chain of reaction. Now we will be talking about the nuclear fission, and we say this is the nuclear reaction happening in our sun. Now let's discuss about the nuclear fission, and this happens with the small atoms. They join to form a large atom. This is the case of deuterium and tritium, which are the hydrogen isotopes. They join to form helium and release energy. And also in this nuclear fission reaction, one neutron is released. Then nuclear fusion is the source of energy from the suns and other stars. Fusion is also a very desirable energy source because one of the reactants, which is deuterium, is unlimited, with seawater being a very large source. And also a large amount of energy can be released with no radioactive byproducts. That is the case of the nuclear fusion. But what happened is up to now there is no any nuclear power plant that produce energy using the nuclear fusion as source of energy. The reason is the conditions to get the nuclear fission reactions are really complicated. Yes, in order to nuclear fusion reaction happen, one of the conditions is the temperature must be high, and also the pressure must be high. When I say high temperature is several thousand of Fahrenheit. Then to get that conditions in one place is really difficult. This is why there is no any nuclear power plant that produce energy using the nuclear fission. And how we can identify equations that correspond to nuclear fusion reactions. And remember, this happens in atoms that are small. For example, hydrogen or helium. They usually in the fusion nuclear equations, we will have hydrogen or helium present in the equations. Then this is the main characteristic how you can identify the fusion reactions. And in this case, we had the hydrogen isotopes, and this corresponds to the electron. Yes, this corresponds to the electron. And here we had two, in this case, we had two hydrogen isotopes. Here we had helium. Yes, we had helium here, and we had, in this case, one neutron. In this case, we had two helium atoms. Here we had a beta particle. Yes, this is the symbol for beta particle, plus two isotopes of hydrogen. This is how we can identify the fusion equation. This is all I had to discuss for today.